Auzubillahi minash-shaytanir rajim. How are you? Was it really announced this lecture? Or was there confusion? You know that there is an NMR workshop in Islamabad and that you are all are invited. Huh?
I am doing work of domestic. What's up? Did think anything about
Yeah. So it means you're not doing. You know, that's what we do everywhere. Yes, yeah. ठीक है? Okay, so yeah, it was very inspiring. I was extremely busy in Malaysia. I met with the Deputy Prime Minister. I had a very long meeting with him, Dr. and many meetings, many ministers. The most inspiring was with Dr. Mahathir Mohamad. He invited us to meet him in his office. You know, he's 101 year old. Okay. We were sitting in the waiting lounge. We saw him climbing the stairs. Stairway. There were two people behind him, including one of his doctor. Probably he treated one doctor along with him. As I'm telling, they're my inspirational, extremely exciting, something which I always think. You know, I met him before as well. I met him maybe like 20 times, but meeting him this time was inspiration. Because many was Prime Minister, he came to Pakistan, place. So, Mahathir Mohamad, in the age of 101 years, was advising comstech how to promote science and technology cooperation in the Western world. And he said, why don't you write me a letter and send me what all the key information about comstech. So I'll try to advise you in every aspect. Truly encouraged. And I presented to him Siddhi Topi. He's probably more and he was so the meeting was sitting with that. That's quite exciting. Walaikum Salam. How are you, madam? Okay. When is NMR workshop in Islamabad? Nobody knows about it? How come on the face of the earth, for people I'm organizing the NMR workshop doesn't know about it? We just wait for a few more minutes. So Aisha, ये जो NMR की वर्कशॉप है, इसका फ्लाइज है मुझे भिजवाइए. पिक्चर होगी ना? Yeah. Okay, so you know that I'm after NMR, I'm going to teach you. I don't know. I'm going to discuss with you philosophy of science. How many of you are interested in philosophy of science? And we will start from very interesting 3000 year BC, back in Alexandria and uh, in Eastern Europe, particularly in Greece, with philosophy of science. We're going to teach you about what is epistemology, what is logic, what is deductive logic, what is inductive logic, what is hypothesis, what are different stages of philosophical processes. It's going to be a mutual learning. I'm not a philosopher, but I would try to tell you, try to discuss with you very unique questions. What is knowledge? And what do you think that what you know is correct? How would you reach to a conclusion? And even funny questions like, do you really exist? What is the proof you have? One of these very interesting problems. And we have a great philosopher with us today. So, okay, so I was going to share one thing. So we are somewhere right at the end of this course, and sadly so, because I wanted to continue this for many more years, but I know that we have a very limited life, not have to move forward. We are now in the domain of two-dimensional analysis, and we are trying to understand that how can we use two-dimensional NMR spectroscopy for getting more information from NMR experiments. And two-dimensional NMR spectroscopy at another dimension in NMR, but also in add-on in your understanding of how NMR can be used. NMR, why you need to record NMR? Because you want to get the structure of a molecule. This is the key objective. So there are many other applications in NMR, but still today and for foreseeable future, the key objective of NMR spectroscopy is to get the structure of an unknown compound. That could be a small molecule or a larger protein, can be of any size. And largely in the domain of organic chemistry, because NMR application and NMR in organic chemistry is not that much, to be honest, because NMR in organics are salts, and often salts, and you're not really interested in salts because you are interested in rocks. You know that sodium chloride, what bond it has? It has no bond. This is a cluster of ions, right? So NMR is not interested in cluster of ions. Who cares? How many chlorine, fluorine, sodium? Who cares about it? But we have molecules of enduring challenges. Think that there was a time when people used to think, study, read, discuss for days and months about the structural density. This was a great topic. There was a time when people used to think how conjugation takes place. There was a time when people used to think of how these 21 amino acids or 20 amino acids?
30.
20 amino acids combine in different combinations to create thousands of proteins. And these sequence of amino acids, how they form conformation, which change their functions. So there are a lot of very enduring questions. And organic chemistry and molecular biology or research in biology is so exciting because you not only wants to have the connectivity. Connectivity is the simplest thing. Which carbon is connected to what, which proton is connected to what. Is the simplest thing. It's not a structure. If you make a structure of cholesterol without any seriousness, no one will ever give attention to it because this is not a structure. In the field of organic chemistry, the structure is one in which you have seriousness, in which you have conformation, in which you have integration. Similarly, in the field of protein, just simple connectivity of various amino acids is just nothing. It just can be done with a very simple technique of hydrolysis by using acid analyzer or now de novo mass spectrometry. You can just get all the information of how many amino acids and in which sequence they are connected. The real structure is helical structure. The structure is when it forms non-covalent interaction and covalent interaction to create tertiary quaternary structure which define the function. Right? Same protein with different post-translational modification form 1,000 different functions. So the actual structure is all this what happened in 3 dimensions. And you start with the simplest one. Which carbon is connected to which carbon? Which proton is connected to which proton? And then you move forward till the end, till you get the full structure. Okay. So this is exactly what we are trying to go step by step. We, in 2-dimensional NMR spectroscopy, we learned that correlated spectroscopy, of course, provide us information about proton-proton interaction through cross peaks, through off-diagonal peaks, which proton is connected to which proton. Simplest information you get. And Toxi provide you information of all the protons in a spin system which are connected to each other. But this is not a structure. A structure is comprised of connectivity, is comprised of carbons. Everything sits on that. I don't know whether in X-ray you have learned that we don't study proton, we just write proton. You read this? You study? Make a structure of carbon and we put proton theoretically on it. It's not that important, you know. If there is sp3 hybridized carbon, it would have you know, and if it is connected to 2 carbon, it would have two protons anyway. Who cares about it, right? So the actual structure in terms of connectivity is carbon-carbon. How would you do that? Right? Inadequate is one. In which you get directly carbon-carbon connectivity. It's not an easy experiment. You can't do it with every carbon because of multiple reasons. Sometimes you don't get that much compound. Especially when you are working on natural chemistry, your global supply of that compound is just a milligram or 2. And you know, no matter what you do, you would never be able to get the inadequate because inadequate is 10,000 times less sensitive than carbon. See that? Because having 2 carbon adjacent to each other is 1 in 10,000. Similarly, even if you have a lot of compounds, you will always would have always a limitation of solubility. You know, in this 0.5 ml of solvent, you cannot dissolve 1 kg of compound. Right? So it doesn't matter whether you have a block of compound, you would only be able to dissolve it a very limited amount of. And on top of it, these people would never allow you to use their machine for 3 days. 1 week.
So I would like, yesterday a student came to me and he wanted to run inadequate. He has quite good amount, about more than a gram, isolated from a plant, and he wanted to do inadequate because he said he couldn't get the structure. I said 1 gram. If you are, it means that you are, the compound must be known. And for spending inadequate the whole week means $2,000 because everything costs a lot. So I said you need to go back and search in the literature. We don't allow proton NMR for known compound, and we want to do it inadequate. Just me.
Be kind with them. Even if it is a known compound, please let them do it. Don't kill their excitement. They're excited. Okay, so eventually we need to find ways of developing this carbon-carbon framework. So the technique which was developed in 1979 was this is called edge detected or inverse NMR spectroscopy. And this inverse NMR spectroscopy is primarily, now you think of my hands, right? This is proton. My hands are proton, my elbows can. Elbows are carbons. Okay. Cozy is, right? So you assume that this proton is connected to this proton through a crosswalk. Therefore, the structure would like this. But actually, what information you need is which proton is connected to which carbon. Right? That is very important. Which proton connected to which carbon. One bond coupling between proton and carbon. Because if you know this proton is connected to this carbon, and you also know that this proton is correlated with this carbon, this proton, then you would know that this carbon is connected to this carbon. I confused you again. No? Okay, if we know that this proton is connected to this carbon, and this proton is connected to this carbon, and these two protons are correlated in cozy, then it means this carbon is connected to carbon. Okay. So what is the most exciting thing to do is to find which proton is directly riding on which carbon. Okay. That the old method was, the oldest method was what? Long time ago, back in 1980, we used to have selective proton carbon coupling. Then there was in heterocozy, proton carbon, super insensitive techniques. So a new class of techniques was discovered which use polarization transfer in an inverse sense. Okay, which use polarization transfer in an inverse sense. And let me read it through. It's a very boring definition. A large number of consequences have been proposed for reverse correlation experiments, which are based on the detection of proton spectrum during T2, that is detection time, while the heteronuclear shift correlation is detected during T1, the evolution time. This type of experiments have been proposed due to the increased sensitivity that one can expect in detecting a more sensitive nuclei instead of the low gamma nuclei like in TAPCO. Now, let me try to explain. I'm a carbon. Okay. Are they visible? Okay. I speak, I whisper, because I'm a weak magnet. My natural balance is also very low. My gyromagnetic ratio is very low. Other is a proton, right? With a big voice, right? If I whisper to him and he loudly speaks, it means that all the information which I have given to him is now open in public. We are connected to each other through a string of bond, which is called a scalar bond. Okay. And literally when I was thinking about it, when I was coming from my home, I remember what used to happen. In masjid, in mosque, when there was a failure of electricity, when there was no loudspeaker available, or even in old mosque when you don't believe in using loudspeaker, considered as Islam. Imam is praying, right? And then there used to be someone who loudly yeah. What the name of this? Huh? Was it Azar? Mukabbir?
Yeah, it's about time.
Mukabbir.
Yeah, Mukabbir.
You know what it? मस्जिद में जब इमाम नमाज पढ़ा रहे होते हैं तो उनकी आवाज पीछे तक जाती है तो एक शख्स की ड्यूटी होती है जो जब वो अल्लाह अकबर के हैं तो वो उसको बड़ी तेज आवाज कहता है and generally someone is selected with the loudest voice in the masjid. The person who is just himself is a by-birth loudspeaker. Okay. And the proton is like this. So, information from proton to carbon, and if proton provide that information, is called reverse detection. Tell you what actually happens. If it is a mirror, proton, mirror, and I am a carbon, I'm standing with mirror, and you see me in the mirror. You don't see me directly. You see me through the image, right? Mirror. Proton is a mirror. So these are proton detected experiments which provide information about carbon. So there is no direct detection of carbon, but detection through proton. Now, why would you like to do that? Question. Why would you like to do it? Let me tell you, in polarization transfer, when you have depth experiment or inept experiment, CH2, CHs, CH3 in different phases. So these are carbon signals, but they contain information about proton. This is the reason why they are up or down, right? If you do exactly the reverse, you transfer polarization from carbon to proton. in polarization transfer, you transfer polarization from proton to make it more sensitive, right? This is called straight polarization. And you increase the sensitivity of signal and you get enhanced carbon signals, which contain some information about carbon protons. Exactly the reverse one. If you transfer the polarization of carbon to proton, right, and detect the proton, no, exactly. This is a question. Why would you do that? Because proton to carbon makes sense. It's more sensitive, right? And then you are transferring the polarization to less sensitive nuclei, like carbon. And as a result of it, you get enhancement. You get sensitivity enhancement, right? But when you transfer the polarization from carbon to proton, you decrease the sensitivity of proton signal. But proton would always be very strong. Even if you divide 6,000, 6,000 times more sensitive than carbon. Even if you decrease the sensitivity of proton signal through inverse polarization transfer, proton would always be much stronger than carbon. That is the beauty of inverse NMR spectroscopy. That you don't detect carbon directly because carbon is bad, not by character, right? Please remember, carbon is very dear to people. A lot of respect for carbon. We are doing everything for carbon, but carbon is what we have inherent problem. But carbon is weak, right? Carbon is weak in terms of its sensitivity, its charismatic ratio, its magnetism, its natural properties. Proton is super strong, 100%, nearly 100% naturally abundant, 4 times more gyromagnetic ratio. You name it, it's a very, very strong magnet, right? If you detect proton and you modulate, if you get information from carbon to proton, and if you see proton, then you get super excellent information about the carbon. It's called inverse polarization. How would you do that? So when limited amount of material is available, the direct detection of carbon-13 can be almost impossible, but the detection of carbon chemical through two-dimensional reverse technique is easy. All HMQC, HSQC, HMBC experiments are proton NMR. Never think that they are carbon NMR. They are proton NMR. This is your examination question. Okay. Why has told them that exam? That was a mistake. It's not your examination. Okay. So HMQC, HMBC, HSQC are proton NMR. They are proton NMR, but information from carbon is transferred to proton. Now through this proton, you get information about it. It's called indirect detection or inverse detection. Okay? Is exactly as you're looking into the mirror, which magnify. You know magnify? Yeah. Right? So proton magnify. Carbon signal, carbon is not directly detected, carbon is detected through the image which you see in the magnifying glass or mirror or whatever it is. Okay? This is NMR spectroscopy. In the HMQC, which is heteronuclear multiple quantum coherent, problem with NMR is that terminologies are so scary here. Heteronuclear, multiple quantum coherence, and he said, okay, enough, let's go home. Okay. So heteronuclear multiple quantum coherence would be obtained in 2 hours, but direct carbon gives 15 hours. If you recall hydrocozy is also possible. We used to do hydrocozy. Number one, we used to isolate a lot of compound. Very simple two-dimensional NMR experiment in which we were detecting proton-carbon connectivity. Right? So we were detecting carbon and we were detecting carbon-proton coupling on two dimensions. So we were getting the spectrum exactly like COSY, but the cross peaks were between proton and carbon, right? 15 hours, 20 hours, 30 hours. Bad because carbon is terribly bad. Carbon is very weak. But if you detect proton, then proton is super sensitive. In 2 hours, or even now less than 2 hours, I'm sure they're doing it less than 2 hours, you get a very good heteronuclear multiple quantum coherence experiment, which is proton-carbon connectivity single bond. Okay, so you are detecting, this is proton detected carbon. You are detecting carbon on its effect on proton. So you are actually looking into the mirror of proton and getting information from proton. There are two types of proton detecting experiment. One is called heteronuclear multiple quantum coherence, which is single bond, and the other is called heteronuclear multiple bond coherence, connectivity, correlation. Heteronuclear multiple quantum coherence is a single bond proton carbon connectivity. Heteronuclear proton carbon, single bond. It means proton connected to carbon. HBC is a beautiful experiment which correlate protons with carbons which are far away, 1, 2, 1, 3, 1. Essentially same experiment. Proton detecting experiment. It's just a filter which you need to add. Called Bird sequence. But anyway, so heteronuclear multiple quantum coherence provides correlation between protons and their attached heteronuclei, means proton and carbon. These guys are so sleepy today. This class is a serenity. It doesn't give you any stress. It gives you serenity. You feel so sleepy today. Today is a stress buster, because it doesn't make sense, therefore more stress, isn't it? Right. Absolutely. Right. Okay, so heteronuclei, these girls are interested in protons. You boys and some girls are interested in carbons. They like to work on nitrogens because they like to work on proteins, and you like to work on organic compounds. So heteronuclear between the attached heteronuclear and proton through heteronuclear scalar pattern. The sequence is very sensitive compared to older headcore. Headcore is heterocozy based on proton detection instead of the detection of least sensitive carbon. You detect proton. The basic idea behind this experiment is in fact related to equidifference technique, which is used to eliminate proton signal not coupled to heteronuclear. This cancellation is made possible. Okay, now let me tell you what actually happens. There are two things happen in heteronuclear multiple function experiment. Number one, that the polarization of proton carbon is transferred to protons. Protons. Now the information in evolution time is transferred from carbon to proton. All coupling of carbon with proton is transferred to proton, and you detect proton. Okay, so you design a pulse sequence in a two-dimensional experiment in which the information from carbon is transferred to proton through polarization terms. So the proton is now labeled or modulated. As I told you last time, that when you exchange information with each other, you are labeled with information. You're modulated, you're not the same person anymore. You have changed forever. It's the first time you have met someone from Nigeria, or first time you met someone from Cameroon, right? And you know about this country, or you first time met with Egyptian and the last time. Sorry. Okay. So this information labeling is important. In this case, carbon information is labeled to proton and you detect proton. And this is the experiment which we perform. You get an experiment like this. So you have two, like all two-dimensional experiment, you have two frequencies. One is proton frequency, and the other is carbon frequency. On x-axis proton, on y-axis carbon. This is the carbon spectrum, this is the proton. Remember, these spectrum which you see on top and at the side are not generated by 2D, they are actually recorded separately. And they just put it there for your reference, for your easy understanding. Now, each peak, this peak, you make a horizontal line and you make a vertical line. Horizontal line connect this cross peak with the carbon chemical shift. Vertical line connect this with proton. It means this proton is on this carbon. Okay? Similarly, this cross peak. Horizontal line, this one. This carbon has a proton which is a chemical shift of this. So you get proton-carbon connectivity. And this is a proton detected spectrum. This is a proton detected experiment that you just got the information about. Similarly, this is my favorite molecule menthol because this is the easiest one. Now I would like someone to come and interpret that for me, because this is the most beautiful experiment one can understand. Lala. Come. Shabash. Anya. How are you? She's our very talented student. Okay, so before Naren teaches, this x-axis is proton, okay, and this is carbon. ये जो है, this is a carbon spectrum, okay, and this is the proton spectrum. So, no problem. Just go up. Now you come to this. You इसको करना है. Okay, this cross two. No problem. You know everything, mashallah. This cross two. Horizontal line है. Horizontal line. किधर जा रही है? 70 watt. Okay. From here, where is that? Horizontal line. What is the chemical shift? 75%. And what vertical line? So easy, isn't it? So this proton, which is at 3.3, is on a carbon which is 73. Okay. Thank you for interpreting. Now next one. Next one. Come to this one. Right? Everybody.
Around
45, 46. Thus, carbon at 46 or 47 is has a proton which is 1.9. Which is it?
1.99.
Isn't it? So, isn't it amazing? Now, you draw this, each one of you. You put it down, you make the structure, each one of you. Look into this HMQC spectrum. And on each carbon, place a proton. Both chemical shifts should be written. Hani is saying that it doesn't have any proton.
No.
Akhi, why don't you just draw the structure? Oh, what? Why are you so upset? Just draw the structure. If you are successfully able to place all proton carbon correlation, you get 1,000 rupees from Dr. Atia. I don't have any money, so I need to rely on people who have money. Just, you don't need to be absolutely accurate, just 34 or 35, whatever you can see. Actually, in interpretation, you make a scale, right? You have a scale. And you have a scale. You use line. Actually make line.
Since we in protein and since we label all carbon and nitrogen, so and in HSQC there are only 4 phase cycling, so 0, 1, 2, 3, 4. So we can get reasonable HSQC in 4 minutes.
Because it's a variable one. You don't rely on natural abundance.
Yeah.
Simple, two things. Straight line, vertical line.
But FUCL number 6, total number also. That's super relationship to proton.
Proton number 6. Yeah, there's a major problem. He's saying that proton number 6 is about 45 carbon, but it has two different protons. It makes sense? No sense. Yeah, because it is atomic protons. There is a chiral center here. There is a chiral center here. Okay? So they are diastereotopic proton. These two proton on C6 are two different chemical shapes. So you see, Hani has taught us that you can identify both protons riding on one carbon if they are two different chemical shapes. Amina, Amna. Now, we want to have tremendous Sudani wisdom guiding us in our life.
I don't know if I understand right. This is carbon number 1,
Okay.
right? Carbon number 1 have the carbon is like 75, right? And the proton, it will be like 3.3 or 3 point something.
Oh,
Okay. Then this is this carbon, yeah?
yeah.
So after that, we are match all of them one by one. Number 2, it will be like 53, and the proton. This is the carbon, and the proton will be maybe one, yeah, 1.11 like this, and we can go to carbon number 7 because it's connected like this, and after that 7 it will be like 28 matches with no? Why? Okay. 25, 26, and it matches with 2. And after that, we can go to the side carbon. It will be 8 and 9. 8 is 22, 23, and the carbon will be, the proton will be is 1.2, 1.3, 1.4. 9, 9 it will be like 15, and maybe 0.2, 0.3. So the chemical shift of this is very low in the downfield, upfield, in the upfield. That means it in upfield. That means it's like shielded too much, right? After that, carbon number 3. About carbon number 3, I guess this one, it will be 27, and number 3, yeah, this one. No. Why that number? Okay, this 23, 1.3. Okay, 1.4.
Another one.
Another one has 2. Why has?
Where is that two? No,
Yeah. This one. This one.
no.
Huh?
Okay,
Yeah, this one.
I'm not even fine. Okay,
Yes, it's number 3. Han is right. My first time to be agree with Han.
And the last time as well.
Okay. There is signal this one. No. Yes. This signals. No correlation with proton alone? Yes.
Yes, because already you see the proton here. Huh? For example,
to connect to which one?
2.3.
Proton. Connect to what? Oxygen. What is proton?
Oh, hydroxide group.
Proton or H. It can be inside.
Honey, OH, there is no carbon in OH.
I mean, if this OH, as we know, because here it's a big dot, it should be here.
Huh?
Because you have another line, which is it should be proton. But this is OH. No carbon here.
Yeah.
No carbon.
2.5.
No carbon. So why it is here not?
Honey, because it's like this.
Okay, so you see, apart from Hani's very interesting question of why OH is not there, I don't know. This is OH and its own will. But anyway, the scientific answer is that OH can be anywhere. It depends on the exchanges. But you see, you can also identify non-carbon containing protons, isn't it?
Yeah.
OHs, NHs, you can identify because you don't find any carbon partner. So this spectrum will not give you the structure. It just give you a table of which proton is connected to which carbon. Class, finish, right? Which proton is connected to which carbon? Now, which experiment you need to connect the structure? Cozy, right? When you know this carbon is connected to this proton, and you have a table of all carbons with a coupling proton partner, then you go to correlated cozy spectrum and connect proton-proton. It means if protons are connected to each other, this will connect to this. You understand? Let me explain to you. In NMR spectroscopy, no single spectrum will give you all the information. It's just like a jigsaw puzzle. It provides information about one thing. This provides information about single bond proton carbon, right? Coupling partners, heteronuclear coupling partners, proton and carbons. So you don't have a structure, you just have a table. I can make a table, you know. Let me just write it through. For instance, I see this one, which is at roughly about 73. Is connected to a proton 3.5. And that's a C6. C6,
45.
44, and then which are 2-1. And 1. So you get this table, right? You get nothing but this table. This gives you information about proton carbon partners. How would you connect them together? How would you connect them together into a structure? I told you that all NMR experiments provide you one piece of information. How would you connect that? You can connect them by using COSY. When you know proton connectivity, you know which carbon is connected to which carbon. Talas, finish. Right? In proton, you know exactly which proton is connected to the other proton. And now you know which proton is connected to carbon. So you can connect carbon together. Any question? Yes.
ये देखिए सर तो 9 नंबर कार्बन के साथ जो प्रोटॉन है वो मोर डिशेडेड है एज कंपेयर टू 8 नंबर कार्बन ये
Methyl. Okay, I think you let me tell you, I who's teaching issue chemistry now? Do you know what enantiotrophic protons are? Diastereotropic prototype facials, diastereofacial enantiofacials. You know? Okay. Can you identify diastereotropic protons? You know diastereotropic protons? Diastereotropic protons are the protons which are present in a molecule where there is already a chiral center. As a result of it, two protons of this CH2 would have different chemical shifts. Two protons of this CH3 will have a different chemical shift. This would have a different chemical shift. These two methods would have a different chemical shift. Right? Yeah, why not? Yeah, because you know why they have a different chemical shifts? I think I need to teach you stereochemistry. Okay. Now, this is C6. Okay. Okay. Now we are moving away from NMR, and we are going into the domain of stereochemistry. Do you know Newman projections? Okay. I make a Newman projection of C6. This is my beautiful C6 with H. Okay. H. ये क्या हो रहा है?
सही नहीं बना।
And two CH2s.
सही बना है क्योंकि यहाँ पर एक कार्बन होगा और पिछला कार्बन उसके पीछे चला गया जो आपने सही बनाया।
Okay. So this is C1, okay? Hydroxy. Okay. C5 is behind it. Thank you. No, it's good to have teachers. C6 is behind, C5 is behind it. Newman projection. C5 has CH3. Okay. C5 has H and C5 has CH2, which is 4. So you're looking into C6, and behind that, this is the PC5. Okay. Now we are discussing these two protons, where they are different. They are different because this proton is between CH3 and H. This proton is between H and CH2. Right? If you rotate it, would they ever be same? You keep rotating it. Can you ever make these two protons similar? Never. Right? Because the chiral center at C5, you can have it C1 also, just to understand it. Chiral center at C5 would never let these two protons be similar. Never. No matter what you do, you keep rotating it. You bring it here, this goes here, this goes here. It will always be different. Understand this? Understand? Yes. Therefore, diastereotopic protons are always different. They have a different chemistries. Now, Dr. Atia will make us this C7 and tell us how this two methods are different. They are also stereotopic methods. Yes, madam, I think we're looking for your wisdom. And Dr. Atia has done her PhD with me, not under me.
Under you.
She said she has done her PhD with me. And I said, no, you have done your PhD with me, under me. Okay, this is a very important thing which you all have to understand. No one will tell you in this way. Make a Newman projection. Try to understand why diastereotopic protons are not similar, never be similar, not even in open chain. This is structure. It can have two open chain, can never be similar. Okay. H. Make a circle. I don't like anything which is okay. Now behind it C2, right? Behind this is a C2. So you're watching this Newman projection from C7. Okay. CH2 has CHOH. Okay. And CH2 and H. Now, these are the two CH3. Why they are different? Why they are different? The environment is different. No matter what you do, it's a free rotating carbon. Is a free rotating carbon with a very less barrier. We keep rotating it. No matter what you do, you rotate this C7, bring the CH3 here, CH3 this here, H here. You do whatever, you would never be able to have this CH3, these two CH3 similar, because the environment can never be similar. Okay, there is no chiron. I would like to commit suicide today. And kindly in my will, if somebody is responsible of that, is this person? Don't worry about that. It's the way you think the life.
Next up, the next up.
Is about
bring the
chirality.
border. We can bring the border. Then
Make the model. But shape, this is a carbon, chiral. This one, and this one is chiral. Anyway, can be anyway, because this one is connected to chiral. And then remember the chiral center can be 50 carbon away or 80 carbon away. You would still have the chemical shift. Understand? No, it can be anywhere in the structure. You would still have these diastereotropic protons having different chemical shapes. Now, what I'm trying to say that this C7, we keep rotating it. When you rotate that, here, or whatever, the two methods would always have a different environment, right? Different neighbors. Therefore, they would have different chemical shapes. Okay? So, this is an experiment, let me tell you. This is the interpretation of it, but what I wanted to teach you is different. This you can get heterocore also. The reason why this is so exciting that this is a proton detected NMR spectrum. And you're getting carbon information through proton. Okay, this is the reason that proton is more sensitive, it's more visible. You get a spectrum in a few minutes, as I mentioned. And it's called inverse polarization transfer, inverse detected NMR spectroscopy. Okay. Any question?
That's why carbon 9 and carbon 8 when asked the same.
Exactly. So this is the reason why CH3 would have, these two protons would have never the same chemical shift. This would have never the same chemical shift. This would have never the chemical shift same. Okay. Similarly, these two metals are also diastereotopic. They will never be have the chemical shift. I think the next stereochemistry course I will take. Okay. No, ask. I'll just take stereochemistry. Yes, sir.
Carbon 5. Constant hydroxide. Assuming carbon 5 is not a hydroxide, what happens to protons of carbon 4 and carbon 6?
Because you still have one carbon center C1.
Will it will affect protons?
Absolutely, because she made this OH here. It can be anywhere. Understand? This is not similar to this ever. It can be 30 carbons away, it would still be different. And all entire stereochemical stereoselective synthesis are based on this factor. The entire stereoselective synthesis is based on this single important factor. The differentiation of polarity at one particular carbon due to. Okay, so any other question? Yes.
You did not directly on this lecture, but you said at the beginning of the class that you are not a philosopher. But I think you are one, so I want to understand how you study and you can relate this to any simple analogy.
Okay, so number one, that to be honest, the greatest understanding and realization of me ever developed is that I know very little. Okay. I know very little about chemistry, I know very little about science, and this is the greatest feeling I have. Number two, how can I be more curious? Is that when I study science, when I discuss science, I try to see the other side. I am self-critical person. When I discuss chemistry with my students, I try to bring points which are not so obvious. Looking into non-obvious is the best talent of scientists have. Obvious is seen to everyone. Yeah. Obvious. I'll tell you a story of Thales. There was a very famous scientist in old. He was from Anatolia region, Turkey, and at that time there was a belief that world is riding on the horn of a big ox. एक बड़े बैल के सर के ऊपर एक रखा हुआ तख्त है. That the entire earth is on the horn, on कहते हैं ना, of a big ox. Okay. And that the earthquake is because this ox sometimes feel uneasy, and when it moves, the earth is moving also at the same time. And Thales was riding, if he was on a boat in Anatolian Sea, and then he felt that the water was moving. It was a very obvious thing. Was moving his boat up and down. So he thought of it. He thought, how come that ox is not affecting the rest of it, and only water is affected? So he then, for the first time, concluded that this is not the ox, but the inner forces, such as water waves, are changing it. Same with Newton. You know, when Newton was sitting, I'm sure that before Newton, thousands of people have the apple falling down their head, right? Millions of people, right? Or apple, or oranges, or why he was able to see this? He saw the non-obvious. It was so obvious that apple always fall down, not goes up, right? But Newton was able to understand that everything falls down because there is some attraction there. And then he discussed the gravity, and there are thousands of examples of people seeing non-obvious. When they see the non-obvious, then they I try to see non-obvious. Okay. Try to see it, know very little about it. But this is how he learned. I'll tell you a story of my father, what he used to do. He used to take me out, and he used to show me stars. And he was an amazing person. He used to ask me questions, and then he never gave me an answer. He just let me think. So he used to tell me, you see the stars? I said, yes. Many of them are not there. Finish, alas. And I keep thinking about it till the next walk with him. that he's saying there's so many stars I see, but they're not there. And then second day or third day, he took me out and he said, there are many stars which you don't see. And finish and tell us. And then fourth, fifth day, and then you remember, this was like 100 years ago when I was a little kid. And then you used to see, and then, after several queries, you used to tell me the reason, which you all know, that there are many, many stars which died millions of years ago, but their last rays is still coming to us. And there are millions of stars born millions of years ago, but their first ray has not reached to us. So they are there, but we don't see them. And there are many stars who are not there, they don't exist, but we still see them. And then his conclusion was, don't believe on what you see. Okay, think beyond it. So when we discuss philosophy of science, we'll discuss about it. Okay, thank you. And Dua.